found those for me. Stole them from my desk. I don't know which one. But did a little more research yesterday, and on hydrostatic paradox, right, or paradox, because Pascal, and there were other people, a guy that wrote in Dutch, but it wasn't the scientific language of the day, so he didn't get credit for it. So Pascal gets credit for the hydrostatic paradox and Pascal's law. I try to separate those ducks a little bit. So Pascal's law says if you have a container, and let's say you put a tube in it and you put a fluid, so now my container's full. Pascal's law will say the pressure in the full container is going to be the same, and it acts perpendicular to the walls of the container, right? So that's Pascal's law. And the problem is we got that hydrostatic paradox that talks about, well, the pressure up here is going to be higher than the pressure up there because of the weight of the fluid above it. And yeah, that paradox. So we're going to ignore hydrostatic, only Pascal's. So there's an experiment that you can do, and I feel like we should do this one. I should add it to the extra, but it's just a whole bunch of work, and I don't know. So imagine with me for a moment. I gotta get a better marker. This is an impressive experiment. Imagine with me for a moment. We have a building. It's very tall, a very tall building, and we have a container that's sealed at the bottom of the container. Okay? And how many stories should we make this thing?
6.
Oh, higher.
600.
6D. We'll go with 60. I'll go somewhere in between them. So 60 stories, which are they 10 foot each? So 600 foot tall. So just for the fun of it. Okay. So now while I'm talking, if one of you would check for me, 600 is pretty tall. No, I guess that's about right. If one of you would check for me the weight of a column of water that's 600 foot tall, you can chat GPT if you want. But as we continue, we have our container. Out of our container, we run a tube up to the roof of our 600 foot tall building. Because it's such a fine tube, I'm only going to draw it as one line that we put water inside of. But that's a very fine tube. You could even say it's like IV. It's an IV size little piece of rubber, right? Tiny, tiny little tube. So we bring to the top of our building a gallon of water that weighs 6 pounds. And because our tube is so small, it's the size of an IV, our gallon of water, we're going to add to it. Down at the bottom of our container, we'll say we have a gallon already. And we're going to say it takes one more gallon that weighs 6 pounds to fill our entire tube, that's IV size, capillary tube, all the way up. So did anybody come up with the number for me?
AI says it's 259.8 pounds per square.
259.8. So we fill that up with 1 gallon that weighs 6 pounds. Because it's water. I'm thinking avgas, thanks. 8 pounds. And pile it. And now I forgot what Ward said. How many? 800?
260.
200 pounds.
260 pounds.
Okay, we put a gauge onto our container at the bottom. And our gauge now reads, after adding 8 pounds of water, 260 PSI. And you say, no, it can't be. That's impossible. And that is the paradox that Pascal ran into. How can I add 8 pounds of water and end up with 260 PSI in my container at the bottom? It's a wild type scenario. So, doesn't have as much to do with what we're going over today, but it's just a review of the paradox. So the paradox is the pressure distributes evenly. The idea behind it is when we have a container, if you have a gauge or an opening, the pressure per square inch is going to be the same on all surfaces. So if instead of a huge container, we just had that tube, well, water per inch high weighs a certain amount. So it's kind of like if you had a stiletto on. There's another video I saw which was kind of funny. I don't wear stilettos, so that's good. Those are high heels, high heels. And if you have a stiletto and put your heel into the ground, all your weight is transferred onto that tiny point. But if an elephant steps on your foot, it's actually quite a bit less pounds per square inch than a woman stepping on your foot with a stiletto. So, if you ever go dancing, don't be afraid of the elephants. Watch out for the stilettos. So, we move on. Just that was a fun thought teaser as we are in hydraulics class. I feel like we could get maybe 30 foot high here with a very small tube and a container and be like, that is crazy. But mathematically it works, and if we don't get to do it in real life, we can say we took a thought adventure, kind of like the trip on the magic school bus. Okay. Today we're doing hydraulic reservoirs, so you guys will understand the principles and designs. In your books, pages 7 through 11, I believe. Not a bad place to be while we're going through the lecture.
Is that the AC 43.7?
FAA 8083-31, the airframe textbook.
Okay.
Airframe textbook.
Was
All
that
right.
chapter 12?
Yeah. Yep.
Oh, sorry.
Chapter 12.
Chapter 12.
I think I have the pages corrected. I was gonna say it might be a page or two off, but I'm pretty sure they're correct. All right, reservoirs, especially, I'll find it as you're finding it. Reservoirs, as the book states from your data, must be large enough. Yeah, it starts right 12.5. 12.6. Must be large enough to hold all of the fluid, plus room for fluid expansion and entrapped air. So the fluid expansion makes sense, right? Stuff gets warm, fluid expands, it's gotta have somewhere to go. So we have a little extra room in our reservoir. And the entrapped air, as we talked about, while we're using our hydraulic systems, we do occasionally get some air bubbles in there and it moves around. And we like a fluid that does not foam, but we get some bubbles, so our reservoir has to be big enough to hold the fluid plus the bubbles. The idea behind that statement is, hint, hint, you would never want to take while you're servicing a reservoir and top it all the way off, because now we don't have any room for our bubbles, any expansion, stuff like that. So don't overfill a reservoir, that'd be a problem. Reservoirs might be non-pressurized, they might be pressurized. Most of the ones around here you're going to be dealing with are non-pressurized, and I picked that word most on purpose because you're all going to be like, yeah, but I only looked at the beach. And I said, yeah, but you should go find the reservoir on the 210, so you're familiar with it. You should go find the reservoir on the Aero mock-up stand, so you're familiar with it. And now my statement's true. Those two are non-pressurized reservoirs, but some of them are pressurized. How about a brake reservoir? Do I get to put the brake systems in the hydraulics category?
No.
Depends who you ask, right? But we got brake reservoirs, and that's a gray area. But you have brake reservoirs that often are run on 5606, so they're going to be similar, but they might not fall under all the exact FAA laws. But it's a hydraulic system and it is a reservoir. They need to be able to supply the operating fluid. Now you might think, well, I'm taking some out with my pump, but I'm also putting it back in. Well, that's not always the case. If you remember that picture from a single acting or single action actuator, where when we put hydraulic fluid in, the backside of the piston just has a spring and atmospheric pressure. So when we operate those actuators, we're basically putting our fluid into the actuator, the reservoir would go down, and then when the spring pushes it back, it's going to refill the reservoir. Think brake system as well, right? When you push your brake, you push it into the brake caliper. When you release the brake, by the beach jet, and it's not ideal, but, you know, leaks happen. So, we need to have enough to deal with the leaks. And, excess fluid, when might we have excess fluid? Back to similar with, let's say, brake system, and the mechanic's working on it, and he takes a C-clamp or whatever he uses, and he squeezes the brake caliper back into it. Well, all that fluid's gotta go somewhere, so up into the reservoir it goes. So, similar situations in, a lot of systems like that. Thermal expansion, we're gonna deal with that tomorrow, I think, when we do, pressure regulating valves. But our fluids do expand, pretty good when they get hot, so, we gotta be able to deal with where's our fluid gonna go when it expands when it gets hot as well. We want a place for purging bubbles. Now, I didn't put these all red and yellow because, well, the whole slide's will be red and yellow. But these first couple slides, it's that type of information. But place for purging bubbles, like we talked about, we get bubbles. How do we get the bubbles out of the fluid? Because we don't wanna have bubbles in our fluid because we want incompressible fluids, right? So our reservoirs are usually gonna have a place to vent any fluids that, or sorry, any bubbles that got in there or air from servicing our system. When we put a new actuator in an aircraft, we're not going to typically, on all the instruction manuals from the ones I've seen, including the beach, we're not going to like crack a fitting and try to run the fluid until it leaks out of that fitting to get the air out and then tighten it really quick. They don't have you do that because number one, we're usually talking a couple thousand PSI. So to have a fitting, like when I say crack, slightly loose, you wouldn't wanna have a fitting slightly loose with a couple thousand PSI and spray it all over because especially with 5606, remember, we said one of the most dangerous things with it is the fumes from the spray. So, normally with our hydraulic systems, we'll seal everything up nice and tight, torque it properly, get the hydraulic system pressurized, and we'll just move the actuator one way, move the actuator the other way, move the actuator one way, move the actuator the other way. The act of doing that, you're constantly resupplying fresh fluid from the reservoir through the actuator to the return, right? It makes that loop, and that's how we get the air out of reservoirs, or out of hydraulic systems back to the reservoir. The beach jet, if you look up the manual on how to swing the gear or after we do the filters, which you will all do, right? So you better be able to find that in the beach manual, or you will find it. It'll say, swing the gear, I think it's 40, 20, it's a lot of times, up, down, up, down, up, down, because they don't wanna leave any air in those lines. It's not twice, it's quite ridiculous how many times you gotta swing the gear. Cheddar.
So, is it hazardous to have bubbles in those hydraulic lines because of what it do to components or because it might expand?
It's not because it might expand, it's because it's compressible. So if you said, hey, we're gonna put the gear down, and it locks down, a lot of systems, the pressure that's in there is the only thing that holds the gear down. Now, some of them will have like an over-centering lock or whatnot, but we rely on that pressure to hold our components where they're at. So maybe a better one would be, let's say the wing flaps. You say you put the wing flaps down, and we're down. We rely on the hydraulic pressure to hold them there. If we have air in with our fluid, and then we hit some turbulence, that turbulence is gonna be able to kind of compress the air a little bit. That's in there, and the flaps are moving around. And so it's back to the whole idea of incompressibility. Yeah, we're the FAA on that one with Skydrol especially, is like, oh, it's it absorbs moisture from the air, which is a problem. I still scratch my head on that one because we really don't do a lot to separate the atmosphere from it. We use, jumping slides ahead, we use bleed air to pressurize our hydraulic reservoir, which is atmospheric air, right? But what they want you to know is, well, don't go pouring water in this stuff, but yeah, no, the air doesn't necessarily damage it, it's just we wanna reservoirs, a place for collecting and separating foreign matter. We often will have a filter right at the inlet to our reservoir or as the outlets of a reservoir. So like the beach, all the filters sit on your reservoir. So it's kind of the happy place they put all the filters. Works pretty well. All right, so this reservoir is missing a few things. We're gonna talk about them in the next couple slides. We're gonna get into some slides that are pretty complicated that I don't expect you to understand. And you're gonna be looking at the reservoirs in them. So you can look at the whole system if you want coming up, but mainly the slides coming up, you're gonna be looking at the reservoir and say, okay, what can we learn about reservoirs from this slide? All right, that's one more slide in though. I don't know how this one got out of order. Pressurized, unpressurized, often be a bleed error, and we're gonna talk about that a little bit later. I think the slide got out of order. The red is just because it's legal stuff, shows up on prep work questions. And the red here talks about if you don't have a pressurized reservoir, you're probably not a fighter jet. Because imagine high G maneuvers, sloshing sideways, all kinds of crazy stuff. And now your hydraulic fluid is not gonna go where it's supposed to go. We're gonna learn about some pretty cool reservoirs today that are hydraulically pressurized, which is like, what? How do you do that? They're cool. It's a cool design. But non-pressurized one, they're not for violent maneuvers. The high altitudes part we'll talk about is it's not so much that our fluid is going to boil. It's not water that if we get too high the fluid boils. But at a very high altitude, there's very little atmospheric pressure, and there's the old saying that nature doesn't suck, right? Pressure is higher pressure on one side than the other. If your atmosphere has very little pressure and you've got a pump trying to run and suck fluid in, well, the reality is sucking is not a technical science term. You always have to push fluid. So if there's nothing pushing on the fluid to push it to the pump, it can't get fluid, and it's gonna what we call cavitate. It'll have little vacuum bubbles on the inlet of the pump, which is similar to your fuel ones. So you have to have atmospheric pressure, basically pushing the fuel to the pump. What the pump will do is it'll bring the pressure down at the inlet of it, so that it's lower than atmospheric. The atmosphere will push the fluid to it. So if you have no atmospheric pressure, the fluid actually won't go to the pump. Because pumps don't suck. Suck's not a scientific thing. It's kind of weird like that. Yes?
So the reservoir is pressurized
Sometimes.
sometimes. Does that mean you don't have the pump coming out after the reservoir?
No, you absolutely will, because we don't pressurize them very much.
So it's not being pressurized to whatever the 2000 is.
Typically not, no. Pressurized ones, I think the highest I've seen, I shouldn't even say seen, I've read about, is 40 or 50 PSI.
Okay.
Basically, it's to get it so that when the pump runs, we're supplying fluid to the pump. And it's back to that. I've always had a hard time with the nature doesn't suck concept, because I'm like, well, all you need is lower pressure. Like we have 2 points, right? As long as it's lower at the pump, then, so if I go into a vacuum at the pump, compared to in my tank, but you start thinking about it, you say, well, what is a vacuum? When we use that word vacuum, we actually typically mean, well, less than atmospheric, right? You cannot go in a vacuum below 0 inches mercury. That's space, if you will. That's a pure vacuum. So if atmospheric is getting closer and closer to space, 0 inches of mercury, because you're flying at 40,000 feet, you can't go lower than 0 inches. There is no such thing as below 0 inches. You can't have negative vacuum. So, makes you go, that's interesting. I can't ever go negative. What you will do is you'll create space, which is 0 inches of mercury as the pump tries to pull, and that literally create space. Kinda cool.
So, when, you know, you pull a vacuum on an HVAC system,
Mhm.
right? And speaking your love language.
Mm,
When I was a little kid, my dad told me,
mhm.
kind of explained the same concept, and I was like, but surely you can get to zero. And he's like, no, zero is like a black hole, basically.
Yeah.
So always, every time we pulled a vacuum, I was super afraid if we like actually, if we actually reached zero, there was gonna develop a black hole inside this HVAC, and just the whole world was just going.
I never thought about it.
Don't let that vacuum pump run too long.
Interesting, yeah. So yeah, pressurized ones, oh, it's actually on my slide, it's my next line, Mr. Ward. Typically 40 to 50 PSI. So, that's pretty typical. As you get into turbines, what you'll start hopefully sink in is usually our bleed air pressure is about that 50 PSI. So I'm touching on it a little bit, you'll get it more, but, so, pretty common, right? 40 to 50, yeah, that's what my bleed air pressure is, roughly. We have multiple bleed air pressures, but the ones we use. Okay. All right, here is the image the FAA gives you of a reservoir. They absolutely, 100% will ask you a question on the standpipe in a reservoir. They like this question because, well, it's one of the easy things they can ask you. So, we have taken our reservoir and sliced it, right in half, which means that this tube right here inside the reservoir also got itself sliced in half. So you're only looking at half the standpipe that's in the reservoir. So you have to imagine with me that there's a tube in that reservoir that is not cut in half. So I'll pass this around. If you look into the bottom of it, it's about 1.5 inches tall in the bottom of there. You'll see the standpipe. So the standpipe is where we get the fluid for our main hydraulic system. That's going to go fluid through the standpipe to our pump to go out to the system. So imagine with me for a moment, blue fluid. Oh, this is fun. What type of fluid do we have today, children? Students? 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 We don't have any children, right? Everybody's over 18? All right, would my pump be able to draw any fluid in if the fluid level was right there? No, it would not. We would be trying to put the gear down or the flaps up or whatever it is, and we don't have fluid available anymore because there's a leak in the system somewhere. So our standpipe is our main system pump. But what we do in our reservoirs is we say, okay, we do that not so much because we don't want to suck the debris out of the bottom of the jar, because let's just try not to have debris in there, right? So that's not the primary purpose, but it might help a little bit generally. But we will have another fitting right at the bottom, and that one gets connected to our emergency pump. So whether it's a hand pump or electric pump. So the idea is you get shot by the enemy and your hydraulic fluid goes overboard, or in your case, somebody forgot to tighten a hydraulic line and your hydraulic fluid goes overboard. You can't put the gear down. The gear won't go down, we're out of hydraulic fluid. What do? So what we do is they will typically have just enough fluid in the bottom of there to operate the gear, whatever system. This isn't like a write it down and quote it, but that's kind of the idea behind it, is there's just enough fluid in there to operate the emergency system of what we got to do. So our hand pump will go, and it still has fluid available to put your gear down. Now hopefully the leak's not in your gear system, or, well, then it's not going to work, right? But that's the idea. It's also kind of that warning to the pilots that you run a hydraulic fluid and the system's not working. Probably if you got to use the hand pump, not a good time to be putting the gear up, gear down, gear up, gear down, because where'd the fluid go? So if you're fortunate, you'll be able to get your required system down and then stop. Don't touch it. Thank the Lord that it went down, and go land the plane. Mr. Ward.
So the main purpose of the standpipe is just to ensure that you don't lose all of your
exactly. So you stated that the reverse of what you'd normally think, right? But yeah, exactly. So the standpipe in there is so that if you lose your hydraulic fluid, you don't lose it all. So, yep, exactly.
So, in emergency situations, I always think of the emergency retraction for land gear. Are we talking just really large aircraft where that's not possible, so you still need hydraulic pressure to release the gear?
A lot of them, yeah. 'Cause otherwise, you might get the gear to like hang there, but it might not go over center. Yeah.
A lot of times it goes out and then there's another lock at the bottom, so it keeps it there.
Yeah, but, yeah, yep, yeah. And hydraulic systems, a lot, it's not only gear, we got flats, we got other, so.
But in this situation, the emergency, whatever's left, you would just use for the gears.
No, it's the hydraulic system still. It's whatever the yeah, it's whatever the pump goes to.
So the pump will operate everything, it's just.
Correct. The hand pump, I'll use the word usually. There's a lot of systems out there, but usually the hand pump is in parallel with the system pump. I'm sure there's cases where they throw it in and make it a little different, but it typically bypasses the unloader valve. So you can like just go past, yeah. All right, Marcy, do you have a question?
Yeah, I just wanted to confirm, so the fluid is coming through the filter neck, tapping fastener, and then.
Yeah, this is a connection where your main hydraulic line would hook up to it, so that's going out to the return. So the fluid comes, wait a minute, I'm on the wrong one. Let me back up. Where's the return? Right there, return line. And part of the reason they put it there, and you'll notice a lot of times, it's not my slide yet, but they'll put it on an angle, so it spins the fluid as it comes in. The idea is we might have air in it, so if we get a little bit of a spin going, the air goes to the middle and can then come out to the top and go out the vent. Now, what's interesting is a lot of times they'll put it in a spin, but then some of these pictures, and they like to say, and then we put baffles, but typically in the bottom, we put baffles to stop the spinning. So sometimes we'll put the spin in so the fluid stays on the outside and the air goes in the middle and the air can come out. But once we get down to the bottom, we don't want this, well, you know, when you drain the bathtub or flush a toilet, you wouldn't want that tornado to make it all the way down to our standpipe. That would be a problem. So they put baffles in, so at the bottom, it's not necessarily spinning, but a lot of times where they dump it in, they'll dump it in on an angle to get it spinning. All right, back to you.
I'm so confused. So what's the purpose of the filter
Oh,
neck if
this
it's
is the
not-
filler like on the beach jet. So when you're servicing it, you're gonna unscrew that cap and you're gonna take usually a funnel or a hose and you're gonna pour new fluid in. And remember how we talked about you are not putting dirt in there. You're not putting dirt in there, Marcy. That's one last place to make sure you don't get any debris in our system. Was it last year or was it the first year we did this? The beach jet was new to us here at SMAC, and we have a sight glass on the beach jet that, let's see, normal fluid line, so their normal fluid line's kind of weird. I would have put the normal fluid line down here. Move that down there, because it's practically overflowing our filler neck, right? So on the beach jet, we just moved our normal fill line down a little bit, because there's a sight glass in it, and we want the fluid to show up at a certain point in that sight glass. We don't want it overfull, because, well, then we're overfilled, we don't have room for expansion, blah, blah, blah. So, we want to fill the fluid to there, but our tank got low because some SMAT student drained it out. Getting ready for the next set of students, right? So, we're gonna come in, we're gonna pour fluid in here until the level comes up, blah, 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 and it's just the right spot. Well, the first year we had this thing, we'd take the hand cap off, and we'd start putting fluid in, and we'd only get about 2-3 ounces, and nothing would show up in the sight glass, but it'd start coming out of the top. And we're like, boy, that's weird. To the point where, rookies, we were actually like, I wonder what's wrong with the sight glass. Is there a plug in a hole? We were, if you you can imagine with me, I've had systems before where the sight glass hangs off the side like this, and they're not actually looking into the tank because there's a line, but there's a cavity and there's like a hole in the bottom and a hole in the top. So we were going, I wonder if it's one of those type sight glasses and our little holes going to the sight glass are plugged. So we almost started doing that until we started reading the manual better and looking close. And oh, sure enough, you take this cap off, and you can do that when you service it. If you reach your finger, hopefully with a glove on it if you're a good mechanic, into there and just kind of pull up, you will pull out what looks like a little cup that's got very fine holes in it. It is that finger screen. Well, over the years, there was enough little debris and dust that finger screen was plugged up. So we'd add an ounce or two of hydraulic fluid, that finger screen would fill up and overflow. So fortunately, we saved ourselves a lot of work by stumbling across. Oh, okay, we gotta make sure that finger screen's clean every once in a while. So, I think that answers the question for you in a very long way, but also gives you something to look at. And there's a little self-confession on. We weren't sure how that thing worked at first. We got a little crazy. All right. Oh, actually, this picture has the funny sight glass. See how you got a little glass gauge, but you're not actually looking all the way into the container? There's kind of a little space behind it and a space up here. Theoretically, if those got plugged with stuff, then the fluid can't get out into that sight glass area. Joe?
I'm assuming those fins are like essentially baffles.
Yeah, exactly. Yep, that's what's supposed to keep the fluid from spinning in the bottom. Okay. So, we will call that standpipe the supply line. The supply line is the standpipe, okay? So, the little one in the bottom of the tank is not the supply line. It's not the standpipe, it's the emergency line. So, standpipe equals supply line.
Hey Case.
Yes.
Sorry, can you go back one slide? So the fins at the bottom, keep it from swirling. Like, what about the fins at the top, like right below the finger?
It's the same idea. Yeah, it's a baffle. Your book talks about them, right? Reservoir system, pump. They're in there somewhere. At least they used to be. All right.
12-7.
12-7 is where the pins, they talk about them? Oh, way back there. They jump around a little bit then. All right. Oh, under reservoirs, yep. All right, next slide. I was reading it because I think I explained most of this to you. All right, all I was saying with my notes on that was we're back to, we're given generalities again, right? So, does every reservoir have a standpipe? Pretty close. You should look for the standpipe. But it's kind of like saying, hey, in Papua New Guinea, everybody uses turbines. Everybody uses turbine aircraft. And you're 99% true, except for Smurfs Aviation. They use AVAs. So, you know, every once in a while we throw in a little bit of a monkey wrench like that. Kind of like our video from yesterday, right? Is it a monkey or an ape? So when we get to the open center first, we want to say closed center, but we can switch it to constant pressure. The first thing you should look for is it open center or not? Because it's not, if it's not open center, well, then it's the other one, which is constant pressure closed center. All right. I actually put on here to have somebody come highlight the standpipe, because it's that important, but I think you guys got it. You got it, Ava? You're good?
Yeah.
This is supposed to be a drawing telling you about the pressure transducers in a system. A pressure transducer means it takes a pressure and turns it into an electrical signal. So don't read too much into this because they've got some stuff that doesn't work. One of the things that doesn't work on this one, if I get a good laugh, Dean's like, the people that do these drawings, well, he doesn't sound like that, I do, is looking at the reservoir. What are some issues we might see with it? Some of you eagle-eyed people. Say what? Oh, yeah, we can't fill it actually, this green line might allow us to fill it through one of those if we find the right spot. I don't see it. The green line might allow us to fill it. So, but yes, you might be right. How about our emergency line? So y'all find the standpipe on here after we talked about standpipes a lot, right? So here's our standpipe. So there's where we typically are gonna draw our fluid in, which means this is the main line coming to my main pump, engine-driven pump. So that would leave this one for emergencies, right? Notice how they drew a little black line across it so no fluid can go through. Now, call me silly, but really, guys? Like, you cut my standpipe in half so that we can see that it's like pipe cut in half, but they couldn't remove the little line here to show us that, yeah, it actually connects to the bottom of the tank for emergency. So it's like, oh, man. So that's the reserve outlet on there. Notice the bleed air system up here. So here's where we pressurized it, pressurized air from our bleed air. When you get into turbines, you'll learn that we would not want to contaminate our compressors and our turbines with hydraulic fluid. That would probably be a bad thing to hydraulic fluid in our turbine engine. So we've got a bunch of check valves, is what those arrows are, bunch of check valves to keep when we shut down the turbines. Anybody know how to make a turbine shutdown sound effect? I was gonna do it. Nice job, Ava.
I hear it all the time at work.
Yeah. So when we're running this thing, we're pressurized to 40, 50 PSI, and we shut the turbine down. Now I don't have any bleed air pressure. Naturally, that air from the reservoir, I had a different word stuck in my head, sorry. The reservoir would go back into the turbine. We gotta stop that from happening. It's so important that we stop that from happening that in our module, we will often have test ports. This one doesn't show them all, it's a different slide. That one of the tests that you do on a regular inspection basis is to make sure that that check valve system keeps any of our hydraulic fluids, contaminated airs from going back into the turbine.
What does ACMP stand for on that supply line that you were pointing out?
Yeah,
Alternating current motor pump.
how'd you get that?
I'm reading your slide.
Perfect. It's actually the next part on my slide. I wasn't 100% sure, I had to look it up, but it's our emergency pump, right? So this is our emergency pump in case our main pump fails. So our emergency pump is basically just an AC motor pump, so alternating current motor pump. It's the emergency pump. I saw Grant's hand first.
I'm a little confused. So if hydraulic fluid is non-compressible.
Incompressible is the technical word we like.
Incompressible, right. When we take the pressurized air off of it, it shouldn't expand.
Yeah, we got all these bubbly, and then even the air in the top of it, you know, we've been in a car wash, I went to a car wash this morning, and even though the water spraying all over me in the car wash is incompressible, I shut the Corvette off. No, I can make it a joke, let's talk about the Corvette now. I shut the Corvette off while I'm in the car wash, because it's a very, I'm gonna use the word humid. There's little water droplets spraying all over the place in the car wash, and they say I got an OptiSpark thing on my Corvette that doesn't want water droplets in it. So, in a car wash, you got all this fine mist that's all around you. So, when you shut the turbine off, you got air in here that's, it's bubbly, all that fine mist.
So more be like gases or an atomized hydraulic fluid.
Yeah, probably, yeah, you're thinking the right idea. Yep.
Okay, but the actual, like, that reservoir will not like fill up and like flow back.
If
just
it
because
did,
the
we'd have a
pressurized
pretty big
gas.
problem, yeah.
Yeah, okay,
But if it wanted to, we're still gonna stop it.
right, okay.
But yeah, think gaseous, misty, yeah.
Is there no barrier between the hydraulic fluid and the pressurized air in the reservoir?
Not normally.
Not really.
Yep,
It's not gonna.
yep. Yeah, like, we didn't talk about accumulators yet, but in an accumulator, there's a barrier. Yeah, no, not normally. Oh,
It's just relying on gravity, keeping it below that line, actively.
yep, yeah. Which makes you go, what if I fly inverted? one has, oh yeah, or low G, like those big jets that do low G, right? Alright, we got 3 reservoirs now. Ooh, we're getting bigger and bigger. So focusing on the reservoirs, notice we're looking specifically for the standpipes. We got more standpipe problems. The drawers. When I was in school at one point, I don't know if it was here or somewhere else, they said there is a big market for people that can do technical drawing. Because you gotta be able to understand the system and draw. It's a big market. So if we start on this one, we got a problem with our standpipe. The top of it, the fluid can't get in. They drew a line on the top of our standpipe. Right? So we come over to this one and we go, okay, I can live with that. I can live with that one. But we come over to the left one and once again they capped off. So, yeah, you know, our technical drawers. But always be looking for that. So ACMPs again, probably that AC motor pump. You could relabel that emergency pump. Just for the fun of it, can anybody find the rat? We'll talk about that in the next slide. We got a little propeller here, says rat. Well, what's interesting on this one is they got the rat pulling fluid off the standpipe. That made me go, that surprised me. I would have considered the rat emergency pump, but, so I don't know if they drew it wrong or if they just said, well, it's not that kind of emergency. When you deploy the rat, it's not because you're low on fluid, it's because your engine-driven pumps or electrical system didn't work. So the rat's not necessarily there for when you're low on fluid, the rat's there for when the engine-driven pumps fail. And I do have a couple slides on the rats coming up.
Or you're low on a different type of benzene or fuel.
Low on fuel, yeah, yep. So, part of that is normally the emergency has direct pilot control. We can turn this pump on, we can turn this pump off. So if I got a leak somewhere, I don't want to overuse it. With the rat, usually once you're like deployed, the rat's pumping hydraulic fluid and there's not going to be a way to turn it on, turn it off. Usually it's just pumping fluid.
Why are there heat exchangers? Does the fluid get that?
Oh man, yeah, and a couple slides or slide shows we'll talk about. The FAA likes to say our hydraulic systems are 100% efficient. We're smarter than that, and we realize there is friction in the system, and friction builds heat, and we got to get rid of that heat somewhere. So, yeah, heat exchangers to get rid of the heat we build. Specifically in like the motors, when we got all these moving parts and we're compressing, and there's especially friction in the motors, the pumps themselves. All right, back to the simpler one. Standpipe is our main supply line. And then you notice our hand pump basically bypass our unloader valve because we're in control of this now. So if our pressure gets high enough, and a lot of systems that are gonna have a unloader like this, an accumulator, a lot of systems will have a pressure gauge for the pilots to see what the hydraulic pressure is. Not all of them, but in modern ones you'll see it, so they'll pump it up and they'll be able to see how much pressure. But worst case scenario, if you keep pumping and you overdo the pressure, because my unloader's not gonna unload. If my unloader normally unloads at 700 PSI, and I'm hand pumping, and I'm all excited because, I mean, I just lost my hydraulic pump. So the adrenaline's going. If I pump it up to 1,000 PSI, what's gonna keep me from going too high? System relief valve, yep. So if I was to overdo my hand pumping, my system relief valve, whatever pressure above the set point will just bleed off a little bit of extra pressure. So that's one of the times that system relief valve, we go, oh, good thing we have that. Marcy?
Is this really like the emergency portion, a hand pump, or it's gonna be like automatic and bigger jet?
Depends how big the airplane is. So our float plane, it's a hand pump. These big ones are AC motors because a lot about 7 days. We're hopefully gonna jack up the float plane, and do some gear swings for you guys, do some demos. And, we'll use the hand pump while we're doing that, and some unlucky student, or lucky student, will get to pump the gear up and down. And, oh boy, it's been a few years now since I've been overseas and done it. I wanna say 100. I wanna say 100 pumps on our float plane to get the gear to go up. So, 1, 2. It takes a while. You don't wanna do this when you're in a hurry. I actually have a video of it later on in this class, not on the 206, but there's a movie. Oh, it's terrifying. They're cranking out a pump.
You have autopilot in 206.
Yeah, we don't use it though. Not much. Tiki.
The emergency pump or requirement,
Requirements. I would not be surprised if it is. You might be able to find that in the FARs. I don't know the for sure answer. The Arrow doesn't have an emergency pump because gravity will pull it down. So, I'm gonna go with no. Based on a guess. Okay, here's a oh boy. I gotta ask Dean. I think it's a G-rotor pump, which we didn't talk about yet, but this is an emergency pump for a hydraulic system. So it would have an inlet and an outlet, and you're gonna, you go in a circle, crank the gear down. So we'll watch a movie where they're basically running one of those. Supposedly this one is in good shape, so we don't take this apart. It's just to look at, and don't make the mistake of holding it and going, oh, here, because hydraulic pumps produce high pressure, and our caps we have on there, not so much high pressure, and there's a little air and fluid in there, so with really only half a rotation or so, you will spray yourself in the face with whatever's inside this thing. Don't ask me how I know.
do you have safety glasses on?
No, I didn't. I was in here teaching, and I picked it up, and I was explaining to the class, and I'm like, you just take the handle and spin it. I think it was mineral spirits, but yeah, I was like, it's a pump. All right, emergency pumps, often hand pumps, might be electric driven, they might be the rat. So here's a picture of the rat hanging down off. It's always surprising to me with these honking huge engines. Ryan doesn't like when I call it motors. Engines. Honking huge engines, that tiny little rat will supply enough hydraulic pressure, enough hydraulic work to do everything we need to have it do. Now, back to how that works is, we'll talk about accumulators later, but it's sitting there spinning away, moving fluid, building pressure, or maintaining pressure. A lot of times when we have the rat deployed, we're not actively like, on all kinds of fluids and stuff. So if we ever had to deploy the rat, we would be careful how much hydraulic system we're gonna use. But at the same time, yeah, it's there for emergency. Now you get into these big jets, and the interesting part is, how often would you really have to deploy the rat? Because usually you got 2 engines, and then even on top of that, a lot of times you got an APU or 2 in the back. Some of those don't do hydraulic pressure, but usually you failed 2 engines and an APU before the rat's gotta go down. So if you gotta deploy the rat, it's a bad day. So ram air turbine is what it is, but basically it's a little windmill.
That's not reverse thrusted. Just
No.
a tiny bit.
When Dean was working in the airlines, they were up in the cockpit doing something, I forget what they were doing, and they hit the wrong button. And the rat goes, "Skoo-skoo!" And they're like, oh, and I can't repeat what Dean's colleague said. Oh, blankety blank, and they run down. Oh, sure enough, we deployed the rat.
Sure enough.
So, I love it when he tells that story. I'm once removed, but we like telling it still, 'cause it's just a little reminder, especially like the beach jet. You don't wanna just get in the cockpit and be like, I think it might be this switch. 'Cause you never know when something's gonna happen that you don't want to happen. So don't throw a switch unless you know what it's supposed to do. Radios on the radio itself.
So when the rack deploys, you can't just put it up easily? If it's deployed in
Depends
a-
on the aircraft. So, in a hangar, if you don't have hydraulic pressure, how are you gonna, like, how are you gonna re-put it up? And if you deployed the rat because you need hydraulic pressure, and then you're getting rid of your power source that would lift it back up.
Right, but you couldn't get more hydraulic in it and
It all depends on why you need it in the first place. Yeah, if you needed it in the first place, it's probably staying down. Yeah. Marcy?
So, I don't know, as logic, I'm a little confused on like why it was bad that they accidentally deployed the rat. Because shouldn't the rat be like shorter than like the landing gear, so it wouldn't touch the
Yeah,
ground?
should be. It's more like the boss going, what are you guys doing? Just hitting buttons that we don't know what they do in this multi-million-dollar aircraft. And then, hopefully nobody was standing underneath it. That kind of thing. Yeah, it could have been a toolbox under there. Yeah. Alright. We're getting close. If we have a pressurized reservoir, we're gonna have a reservoir pressure relief valve. Some of the non-pressurized ones, no, they wouldn't have that. The non-pressurized ones are just vented to the atmosphere. So they want you to know if it's non-pressurized, there's gonna be a vent to the atmosphere, so it doesn't get pressurized. If it's a pressurized reservoir, just in case it gets over-pressurized, there will be some sort of relief valve on there. There'll be a sight glass. They like to have a sampling valve on them. Back to, they like this term, I think it was a prep work question. Usually they might give you this, and then they'll throw a couple on there that are not on a reservoir, and you gotta be like, oh yeah, no, I don't expect that to be on a reservoir. So our common components that are on there, grain belt, temperature transducer, so we know what temperature it is, and sometimes even quantity if we get real fancy, right? So the pilots, while they're flying, don't have to send somebody down to look. That'd be pretty hard to do in the beach jet. So some of them won't tell you. There's the blown up image of just our reservoir, basically test port that's got the check valves in it. So that's something that, as a mechanic, if you're working on big aircraft, you might have to do the test eventually on. If you were ever to do that, follow the instructions. The instructions will typically say when you vent the pressure to use a rag on it. And actually, more to the point, you might have a pressurized reservoir, say the beach jet, if it was running. So say you're servicing a jet that came in at the FBO, the instructions will often either say take it off very, very slowly, or they might say use a rag on there. Back to if you're up in the tail of the beach and there's some pressure in there and you go kind of like your radiator in your car. Not so much that you're gonna get burnt, but back to the fumes. We don't want all those droplets getting in the air. Do you breathe them? So if you have a rag on it, it'll keep the fumes from spraying, not fumes. It'll keep the droplets from spraying out. It'll catch on the rag, and then you won't breathe the droplets. You don't want to breathe droplets. All right. Let me blank this a minute. I think we only have 5, 6 slides left. Yeah, we'll just go through. What do you think? 5-minute break? It's Friday. Let's take a break. Let's do a break. We'll come back, because this is kind of important. So 10-minute break, I bet, and so goes the junior. Come back at quarter after.
obviously, here's the support rings. What O-ring is damaged, 23 or 24? Did you ever figure that out?
10. Come back at quarter after.
Is the closest. Okay. Well, I think I was confused, because I'm like, is the top support? Well, I did have a question about lower support. Why
About
are
what?
we putting in, for the logbook entry, why are we putting in that we specifically changed this one on? We took everything apart, we should be changing all the O's automatically.
Or it's pressurized.
Yeah.
Caught me.
So, yeah. But this system does.
I mean, I submitted it anyway.
Yeah.
But I just thought that was.
That's a very good catch. The actual reason was, I was trying to make it easy
Oh, no,
on you.
like a manual valve.
We're trying to make it easy on you and not list
Pressure.
every O-ring in the
Or
whole
like
thing.
a relief valve.
I think,
Yeah.
and is that something you
But
couldn't
it's just not too bad.
block with, like every single O-ring?
Yeah,
Like,
because
it's not
we
pressure
wanna make sure you did the right ones. If somebody looks at it after you, so if they have a failed O-ring and they're like, did they do the right O-ring? Cause once they're out of the package, it's pretty much impossible to tell. There's no part number on an O-ring. So at least they can look back and be like, what part number O-ring was this? Oh,
You got more out there?
yep, they did the right O-ring. Or, oh,
If
no.
they did, I'd have both of them.
So the O-ring guy was 329.
Mr. Case,
Yes.
so vented,
Stuck on
okay,
one.
so just for my
Yeah,
clarification,
I asked him that.
Who is a bad picture basket?
right,
I think honestly, it'd be easy.
pressurized
Okay,
means it's a
You
sealed
should've just
reservoir.
said, put,
And,
replace
Yes.
all
and then
O-rings,
non-pressurized would mean like
have
vented
that
down,
stereotype
like you always
thing
have
on
vents
this.
Yeah.
going there,
Just
okay.
did all.
And then if it's pressurized, could you still have like
Oh,
a
true.
relief, but it's like a
Every,
regulated relief?
exactly. Yep, anytime you use the word relief, there's gonna be
Or what?
a set point of sorts, right? It's gonna be, hey, this will relieve at 60 psi. So when we use the word relief valve, there'll be a certain pressure that it opens up and goes at, where a vent is typically just gonna be open gas. Especially if we use the word
Right.
atmospheric vent.
Okay.
But I never
We
got to
have,
do any of the logbook anyways.
so this one says a connection line
So I
pressurizing.
supposed to replace all of
Yeah,
Now, this doesn't have the
what goes in the logbook.
relief on here,
but that would have,
but either on the tank, or it might be on that line. Let's see if I can get back to the picture we were at. Relief actually on here. Gauge, reservoir pressure switch.
we have a manual bleed valve.
Yeah, that's manual, so no, it doesn't have it. So
Okay.
probably in between here and the reservoir, you're gonna have a relief valve.
Okay, right. Could you go back to that other picture of the reservoir thingy? So I was just wondering, like, I'm having trouble understanding the nature doesn't suck thing.
Yeah,
Because, in my opinion, gravity would just make you so you always have oil, no matter how high you go.
yeah,
You
so
know what I
say
mean?
we're hooking a pump up to here,
Right.
and we're gonna say it's a big pump
That needs a lot of
that needs a lot of fluid.
fluid. Okay.
So we start running this stuff and we get so high that, let's say up here is only, we switched to inches, only 2 inches of mercury.
Okay, so not
And
much.
Not much pressure.
At all. You're
Now my
almost
big pump
space.
is drawing a ton of fluid out.
Okay.
It can actually draw it out faster than
Than gravity
what our
would.
gravity would flow
Okay,
through.
and that's when you start doing that like bubbly thing that
That
makes a
we
problem.
call cavitating.
The cavitating.
Yep. I saw a video that I wanted to try, but haven't got around to it. The guy has a glass bottle with water. He
Okay.
takes a rubber hammer and he hits the top of the bottle. And if you look really, really close at the bottom of the bottle, it looks like bubbles appear. And you're
From
like,
the cavitating.
from the cavitating.
Whoa, okay.
No, that's, I think he had water, so some people would be like, oh, he reduced the pressure enough that it boiled, which
Right.
probably would happen before it cavitates with water.
Okay, well,
So
it would
it'd
be
be
same concept.
Same
of, like,
concept though, right?
Like pressure, bubbles,
Yeah.
NASA spacecraft going into 2 inches of mercury.
Well, not even NASA, just you start flying at 40,000 foot, 30,000 feet, there's not much pressure
Sure.
up there. It's,
Okay.
Here, we'll look it up real quick.
Yeah, I think, I mean, I don't even know.
I wanna say it's a third is all, so you're only talking instead of, basically 30 inches of mercury where we're at, it's like 10.
Okay.
Atmospheric pressure at 30,000 feet. Shows up in the chart later, so you'll see what it says. We're a little slow today. I should've
Yeah,
Googled it.
that's like, yeah, that goes down pretty quick. And that's, so is there usually, I don't know, an atmosphere that everything above that would be a pressurized system? Is that what most people,
I
is
think
there a line?
once you get to like jets, right, so you start going in a nuclear jet and then you're. interesting, like, right? So for instance, is the beach,
You have a depressurization, you lose hydraulic pressure.
yeah,
Window gets open, what's it say?
third, yeah, it's a third, so basically you're only 8.9,
Yeah.
you're only
Yeah,
9 inches, and that's at 30,000. Some of our corporate jets are flying up at 35,
Yeah.
maybe even 40 for some of the new ones. So yeah, it's not much pressure. Now, yeah, obviously if you're not running too fast, it's enough that you'd say gravity, but
But it
turbine,
would be safe to have that pressure. Okay,
pressurized enough.
that makes sense. Now, I have one more thought.
Yeah,
If you're trying to get the bleed air, or you're pushing air out of your system,
yep,
and it's a pressurized system,
yep.
when it's sealed like that, wouldn't you get into problems of like you're adding more air into the system as the air comes back and you're moving hydraulics? That mess up like the pressurization, would you like repressurize it?
Back to, that's why, that's a potential reason why we have a relief, right?
Okay, so that would take care of that.
The relief, if we draw air back, it's, we have too much. Now, if there was air out in the system somewhere, the interesting part with that one is, we're not really gonna get to a point where, oh, my air came back pressurized, because you had to have fluid take the place of the air. So,
Right,
so we would just trade places and put fluid in the air, so.
right, okay, so you would still maintain pressure, you just would wanna like refill your fluid.
Yeah,
after.
you'd go look at the reservoir and be like, oh,
Yeah, okay.
my reservoir is low. So that would actually be a bigger issue, and that's why like on the beach, they're gonna have you swing the gear 20 times. Get all the air out, and then they'll say, okay, resurface the reservoir. Just make sure it's
Grant has like almost the exact same one.
No, that makes sense. Awesome, thank you.
Yep.
Morning, Case.
Hey, I'm gonna see if I can pull it up real quick.
Mine has the cool silver.
We'll see if it actually shows up.
I like it. I think I collect them.
It's not my idea. We know a spot that we want to take my dad.
You can change it up based on your mood. Like, okay, I'm gonna mess it up today. No, I want this one.
They're like, oh, it's been cold enough for it to freeze. At least close.
58.
It's pretty close to that. Yeah.
That's better than it was.
I go to it is. We have color. And it gets spinning.
Right? Solid. So you'll be like a black light, so you'll watch there. Yeah, no, I'm going to the church.
That's the one we just saw. Don't be on dynamic.
Failed you, bro. I was just seeing what you were doing tonight.
So some of those, it was. Okay. Oh, yeah. Thank you.
It might be better if you actually see the screen because you have actually blue.
Yeah, my problem, I don't like the screen, I don't want it smaller.
You cannot write over it.
And you can't write over it.
So this is going in, this is going
Actually, I might go back to that one that said white. See that?
So I think it was the photo of the
I'm a very passionate person. I like my plates to look like this. I like it. I like it. And so we should, yeah. I like making sure that all the, and then
Try that for a while. Thanks. Oh, shoot, did we have Sozos in there?
Yes.
Hey, we can extend it.
I'm good. We only got like 8 slides. I'll head in there after the next 8 slides. All right, welcome back. We'll get back in so we can get back out.
Yeah.
shows up in a couple slides coming up, as somebody, Randall, I think, brought up to me right before break. Uh-oh, I forget who you brought up right before break. Oh, yeah, if the reservoir is in the cabin, if it's in a pressurized area, sometimes they won't pressurize the reservoir, because they're like, well, it's in a pressurized area. And then you all go, well, what if the cabin loses pressurization? We go, yeah, well, we got a problem again, don't we? The prepware somewhere, your book does like to mention that if you have a jet or a high-flying aircraft, sometimes they'll put the reservoir in the cabin, and I think they're just kind of covering their tail for people saying, wait a minute, it's not pressurized on the XYZ jet. Okay, well, they stuck it in the cabin. So, yeah, there's always exceptions to the rule. Okay, so this is a fluid pressurized hydraulic reservoir. This is the drawing the FAA gives you. Terribly hard to understand. It's pretty much the same as this one, just flipped upside down. So we're going to look at this one first that I grabbed from online, so we understand what's going on, and then we'll move over and try to get everybody to say, oh, okay, I see what's going on there. So what we have is we have our fluid chamber here that goes down to our pump that is going to send fluid out to the system, right? Notice they even put a nice standpipe in there for us. That was nice of them. Not that it matters if we're flying inverted and have a fluid pressurized reservoir. So they did good, and then we go, man, we got a fluid pressurized reservoir. But okay, whatever. What we want to do is have the fluid going to the pump be pressurized, right? So we will take our high pressure hydraulic fluid, which, it doesn't have to be pressurized on the ground. So once we start the aircraft on the ground, we have hydraulic pressure, so we can do this. So we start the aircraft, we put hydraulic fluid in here. If we raise the pressure, that's going to want to move this piston here down, right? It's going to move it down to this cavity. Maybe we could put a vent on here to make people happy, or maybe it's hydraulic fluid. They didn't draw that. So that force pushing down is pulling on this piston, causing this to be pressurized. So if we wanted to do some fun math, we could say this piston has a 5 square inch area, and this piston has, why am I gonna write that on there? Has a 500 square inch area. Seems like my math is off, but I think what happens is the smaller one usually is like a 1 square inch area. So if I put 3,000 PSI on, I feel like I'm backwards. No, I think we're right. We'll do the math. See, that's why you should always do the triangles. 3,000 PSI on this one, what pressure will that produce here? So we'd come down to this, and we'd do our triangle, and we'd say 3,000 PSI over 5 square inches is going to be 5 times 3, 15,000 pounds. Oh, that's a lot of, I think I made my piston too big. 15,000 pounds worth of force. So then I come up to this guy, and I say, okay, I got 15,000 pounds worth of force pulling the piston down, but I got to divide that out by 500 square inches. So 15,000 divided by 500 is 330 or 300? 30. All right, so I got my ratio close. My reservoir got a little bit big on piston size, right? Because yeah, 500 square inches that's a big piston. So typically you're probably going to have maybe like a 1 square inch here and maybe 100 square inch. So that is how we pressurize our hydraulically pressurized reservoirs. You guys good with that on this side? Following me? Okay. And obviously we could have a system that will adjust the pressure here based on what we want here. So it might be adjustable. It might just be, well, we know we got a 3,000 PSI system, so we're going to use that. A lot of options, but that's the idea of what we're doing. so that when I fly inverted, and then picture this one being totally full of fluid, right? A lot of times we're not going to want any air in these systems. If we get air in there, but a lot of times they will actually have a way to get the air out. But that's totally full of fluid, and we go inverted, no problem, because we're not relying on gravity anymore to force fluid to our pump. The hydraulic pressure is actually forcing the fluid to our pump. So that's why we like those systems on that type of thing. You do have a homework coming up. It's my next slide. I'll show you on a helicopter that has one of these. I think actually our Bell helicopter has one of these, which may or may not be part of your homework, to figure out kind of the system. So we move over to here. Same system. It's inverted. What's tricky is this whole piston here moves. So as I add pressure to this, basically what's going to go on, and then right in here they failed to draw our O-rings because that is actually a joint that slides. So if I add hydraulic pressure to the green, what's going to happen is this compartment here is going to try to get bigger. And when that compartment tries to get bigger, because I added pressure to it, this whole piston is going to move up, or try to move up, compressing our fluid in here out to our pump. So they definitely could have done a better job drawing that one, but you get the idea. So this one's easier to understand. It is what they drew upside down. It's just they really should have gave us some O-rings to allow movement there. My understanding is some of these systems, because part of that piston moves in and out of there, some of them will actually tell you how much hydraulic fluid do we have in here, because we don't have a sight glass on most of these anymore. So what they will do is, like, one of them will give you, I'm going to essentially say a measurement there, and they'll say you want that piston sticking out of the hydraulic reservoir a certain distance, and then you know you have the right fluid. Because if it gets low on fluid, this thing's going to get pressurized, and all of a sudden now we're sticking out to here because this whole piston moved up because I got less fluid in here, and they'll go, oh, that's what's going on. So that's a pretty common way to check the fluid level in these is you're looking at either how far the piston is sticking out, or they'll give you essentially a sight glass mechanism for that. So here's an image off your homework that's pretty similar. And this one, it's laying sideways, if you will. And Sikorsky, I think. I don't know how to spell Sikorsky, so messed up in my PowerPoint, Mr. Ward. Or I have it right, and spell check doesn't like it. So one of your labs has you say, how do I know where I'm charged at? This line between red and black right there, that is the indicator line. So that's the line where they're saying, where is the indicator line? And they'll give you instructions, and they'll say, hey, if you're lined up with the black, you're maybe good, maybe bad. If you're lined up in the green, usually green's a good thing, but you might be good, right? If you're lined up with the red, well, so we don't know if red is good or black is good, and that's part of your homework is to be able to go in and say, where am I at? That is not hydraulic fluid. That is basically an indicator on the piston that's moving to say, hey, how far is my piston protruding in my hydraulic pressurized reservoir? Isaiah?
So how does this, maybe I missed it, but how does the system like reset for, I'm just confused on, if it goes down, how are we going up at all?
Yeah, so maybe a better way to phrase it, if I go back a slide, we're after pressure, not necessarily movement, because hydraulic fluids are incompressible, right? So the difference between having my fluid that's going to go out to my pump at 0 psi and 50 psi, because it's incompressible, really it takes no movement to do that. I'm incompressible. it just takes a certain amount of force. So in a perfectly balanced world where if I move my gear or my flaps, I'm gonna pull fluid out, run it through my pump, run it through an actuator, and then run it back into the return. So in a perfectly balanced world, that thing's not moving. But we're holding it under pressure so that we supply fluid to our pump. If we have not a perfectly balanced world with a little bit of changes, yeah, this might move up or down a little bit, and that's back to 30 to 50 PSI is not gonna be any resistance at all to our pump that might pump at 3,000 PSI. It's not gonna have any problem on the backside of the actuator returning the fluid into 50 PSI. Because we're talking typically pretty high pressure pumps. Even if it was only a 500 PSI pump, it's not having a problem overcoming 50 PSI to return fluid back into there. I think that's basically what you were asking.
And then, I guess when you're filling the reservoir, then
Yeah, tricky. So usually it's a hand pump. Usually it's a pressurized hand pump. When you look on, I think the Sikorsky, if I'm not mistaken, they have you pressurize the thing up, and then with a hand pump, they have you add it until it's the correct level. It's been about a year since I graded your papers, and I'll admit, I actually haven't reviewed how to do the Sikorsky, because I'll wait till your papers turn in, and then I'll pull the grading sheet out. But that's for you guys to figure out, and me to find out you don't know what you're doing, or you do know what you're doing. But yeah, basically, you're gonna have to, essentially, up to say 50 PSI, yeah, you gotta force it into there, right? Now, when the aircraft's not running, I don't have a pump providing pressure to this. I theoretically don't have any pressure to fight as I'm adding fluid, right? But that's part of the Sikorsky's, they're like, how do we, so that's one of the things you guys get to look up in your lab, is the process for adding fluid to these. But yeah, typically you're pumping, you're not pouring, because pouring, there's no air in there, there's no way, yep. One of the reasons you're pumping as well is the pump that you're pumping from, you gotta keep your level in the, I'm gonna use the word the reservoir in your pump, high enough that you never suck air in it. So, we try pretty hard to make sure we don't get air in these systems. Alright, servicing. Oh, I'm supposed to read this. Page 1211. Starting right above that picture that we just showed you. Reservoir servicing. Non-pressurized reservoirs can be serviced by pouring fluid directly into the reservoir through a filler strainer, like we talked about, Marcy, or a finger strainer, incorporated within the filter that will strain out impurities as the fluid enters the reservoir. Many reservoirs also have a quick disconnect service port at the bottom of the reservoir. A hydraulic filler unit can be connected to the service port to add fluid. So basically, as we get fancier and fancier, and the beach has this, a lot of times they'll actually have quick disconnect fittings, so that instead of taking the cap off and pouring fluid in, you can, while the aircraft's sitting there running on the tarmac, right? You ever do this? No? While it's sitting there running on the tarmac, you can be like, oh, we're a little low on fluid, and you hook up the quick disconnect hoses and add a little bit of hydraulic fluid, disconnect your hoses. The quick disconnects have check valves, we'll cover them later, so that as you connect and disconnect, they don't leak all over the place. So some of these reservoirs actually have a fitting on there where you can pressurize fluid right into it while everything's running. So kinda nice, kinda handy. And that's what it's talking about in that paragraph where it says aircraft that use pressurized reservoirs often have a central filling station in the ground service bay to service all reservoirs from a single point. So back to that slide where we had that had 3 separate reservoirs on it. A lot of times if they have that, they'll have essentially a reservoir that you add fluid to, or pump it in, and then from that reservoir, you'll add it to the other ones. They try to make it easy on you guys. I'm skipping a bunch, and I'm going over to top right over here. I try not to read out of books much, but some of the more important ones that show up on tests. Before before servicing, always make sure that the spoilers are retracted. Landing gears down, landing gear doors are closed, thrust reverser retracted. Parking brake accumulator pressure reads at least 2,000. Why would we care about that? Any guesses? Try to get you guys to exercise your brains here.
This is so that the fluid isn't drawn up in there and it's actually in the.
That is exactly the idea. So, stuff like spoilers, some of those other things, they might be single acting with spring returns, that kind of idea. So, the book's being a little bit vague there. Vague. The book's being a little bit vague there. What they're saying is follow the instructions for servicing the reservoir. When you do the Apache, there's a specific way you service it, and actually you'll fill it until it's piddling basically on the tire onto the floor. So we got to follow it, and they'll tell you to have the gear in a specific position and the flaps in a specific position. We're going to cover actuators in another class, but imagine with me for a moment that we have an actuator that has a line going out, and we're connecting to the gear or whatever it is out here, and there's a piston in the middle of here, and we've got a port here and a port here as we're pushing fluid in and out. If this piston is all the way this way, not as much of the actuator body is taken up with the shaft. So I have more fluid in my actuator right now than when I move the actuator all the way this way. Now some of the space in my actuator is being taken up by that shaft. So that is not a balanced actuator, and we'll deal with that when we talk about the actuator class. We'll even talk about how the force that you can produce is not equal on these either, right? So the instructions will tell you very specifically, do I want the flaps up or do I want the flaps down? In this system here, for instance, this might be flaps up, and if I go to service the reservoir with the flaps up and I top it off, I put it to the line you should be at if I service it, and then I go put the flaps down and look at my reservoir, I'm going to say, oh, I got less fluid in my reservoir, because whatever space that shaft was taking up, I'm now that much fluid low in my reservoir. So you always follow the manual, put the hydraulic components in the configuration they ask for, because especially with unbalanced. Just to catch one question, some of these they get real fancy with, and they'll put a shaft all the way out that end with an O-ring, and they're like, now we're balanced. And basically, it's a waste of money and time, because you don't gain anything other than balance. You actually lose a little bit of power on the one side, so they don't do it much. Check.
In this drawing, which side is the hydraulic fluid on?
It's on both sides, depending on which way I want to push my actuator.
So how's the rod? Oh, I guess in this one, then the other one. But there's only a rod on one side, that's where you get.
So if I put high pressure here, it's going to draw the rod in. If I put high pressure here, it's going to push the rod out, which is how we have it longer. I guess I didn't draw my rod getting longer and shorter. We'll cover that in actuator class. Yes?
So that piston must be like pretty tight against the side.
Yeah, there's O-rings on it. There's at least one O-ring on there, maybe more. Yep. Okay. Here is the Piper manual on how to fill it. I'm not gonna read it all to you, because that's part of you guys' job, but basically up in the nose of the Piper, there's a panel that we can take off and we can add a line to. So we gotta access that door, remove the side panel. We gotta put the airplane on jacks. Oh man, just to service the reservoir? Yup. But we're going up anyway for a bunch of your labs. Remove the filler cap, and there's a little elbow that's like stuck in there, and they're like, well, it's stuck in, you can't connect it that way, so pull it out. But Ryan will help us with that, or me while I'm out there. It says disconnect the pressure and suction lines from the pump and connect them to an outside source. We would call that a mule. So you'd hook a mule up to it, and you'd go, because it's saying turn on that auxiliary source and basically fill it until it overflows. It's an interesting way to do it, and it's going to leak back behind the front wheel, and then once it's full, what does it say? Basically turn it off, but you're moving the stuff. I'm going to stop there so you guys have to read it, but it's not quite so easy to service the Apache. It's jacked up, you're putting the flaps in the right position. What we have found is we can, instead of disconnecting the motor on that one, there are a couple different ways you can do it, where you can add pressure to basically I believe it's the relief line, that elbow we turn down, and we can leave the pump connected and just add fluid that way. So once we get it jacked up, if you have the paperwork out there, we'll go over it with you. But there's a couple different ways to do it, but it's going to leak all over the floor. So it's a little bit of a mess, but read this, familiarize yourself with it, and then once you get out there in real life, you'll see it. When you're on the troubleshooting one, just another reminder, follow the troubleshooting steps. A lot of manuals have troubleshooting charts in them, and you're going to follow the troubleshooting chart because it'll say, well, make sure that the system has fluid in it. You'll do that. Okay, make sure that the hand pump works, and you might pump the gear or the flaps or something. You'd be like, oh, okay, so we can build pressure, and then they'll have you check systems. If you don't follow the flow of the chart, you might start going off on a wild goose chase saying, oh, we're out of fluid, or there's a monkey in the can, and he's plugging a hole or something. But if you follow the troubleshooting chart, it usually goes pretty smoothly. That's why they do them. The other one is, I've heard, you saw the beach jet where Ryan's got that thing that he pulls the pump off, he puts that box on, and that box spins the pump motor. On the Apaches back in the day, they used to just pull the pump off, leave the hydraulic lines on, and they'd hook a motor, or a drill, excuse me, to the pump, and basically do that same thing, and use the system pump to power stuff up and down. But yeah, that way you're not pumping all day. While we're out there, we're going to try to leave the pump on the Apache for the most part, unless Ryan directs us to take the hoses off. You guys have where you have to change the hydraulic pumps on the Aztec, right? It's one of your labs, replace a hydraulic pump. If the line gets too big and backed up, we can have somebody replace the hydraulic pump on the Apache, but we're trying to avoid that because it gets congested over there. But if you're in that group and you're like, we're rock stars, we can do this, ask Ryan or whoever's with you, say, hey, can we do where we disconnect the pump? There's multiple ways to do it. Okay, here's same chart. See, they give you the optional use of additional test equipment, which has many capabilities. And basically, they're saying you can, where is it? Test unit. Disconnect the hydraulic pump hose from the fitting in similar situations. There's multiple ways to do it, but even with a test unit, they have step-by-step instructions to do it. So we'll see which one we end up using, what one Ryan wants. I don't want to give too many instructions because I'm going to kind of let him decide, hey, which one do we want to do, and have you follow the instructions on it. All right. This is a picture of the 210 reservoir. Notice here's my hydraulic pump on the 210, because it's a power pack that we didn't cover yet. The reservoir sits kind of underneath the pump, and the picture didn't come through very well, but there's a little cap, I don't know what you'd call that thing. It's not a valve. It's one of those ones where when it's down, it squishes the rubber out, so it plugs the hole and the plug's nice sized in there. If you lift up this lever, then you can pull that plug out. I believe on the 210 it has a dipstick, so I purposely didn't give you an amazing picture, so that you go to the service instructions and say, where in the world is the hydraulic pump on the 210? So that's one of the ones, but thought I'd give you the picture so you at least have a little bit more idea once you find it that, oh yeah, I found it. What is that? Anybody got an idea?
Brake cylinder.
Brake cylinder. I'd like to say it's a reservoir. The FAA agree. So not so much cylinder, but it sits above the brakes and it holds extra brake fluid, holds extra 5606 for the brake system on our small Cessnas. So I'd like to call that a reservoir. There's no piston or anything in there. It just holds fluid at a certain level and then goes down to the brakes. So
The brake cylinder looks similar to that.
it does. And actually, these are typically mounted right onto them, or very close. And there's a lot of different styles and systems, but, so yeah, so I would kinda call that a hydraulic reservoir, but, notice no standpipe, no fins, no reliefs, so the FAA probably says, that's not a reservoir, gray area.
Harbor freight reservoir.
Harbor freight reservoir, yeah. All right, that's what we got for today. Take a break for safety. I'm gonna open up lab 4, and you got labs 1, 2, 3, and 4 that you can work on. Highly suggest we get a clipboard and start going in groups of 2. 2 would be good. Certainly